Okay, in this section, we will be learning how to integrate slightly more difficult functions using a method called integration by substitution. So this is essentially the opposite of the chain rule. So we are dealing with composite functions. So this is the rule right here for the anti-differentiation of a composite function using so it's integration by substitution. I usually call it U substitution, and you'll see why in a moment. So this is the rule right here. I'm not going to read this to you because it makes things a little confusing. I think once you see the examples, you'll sort of see what we're doing here. But essentially, you want to look for a piece like sort of the inside of a composite function where when you take the derivative of it, the derivative of that is somewhere else inside this whole function. And then we would call that U. So here, this is g of x, and we're choosing that because there's g prime of x over here. So we let u be g of x, and then when we take the derivative, that derivative will also be substituted out. So you'll kind of see what I mean in a minute. So the key to solving any U substitution problem is to look for a U function whose derivative will match up with other parts of the function. So what we're trying to do is simplify the integrand. Again, the integrand is the function inside the integral into something that we've seen before, so that it turns into an easier function and we can just use the power rule. So this first example here, so this we definitely can't use the power rule. We have a composite function here. So we're going to look for, typically it is the inside of the composite function. I don't want to say always, but you'll notice that the inside of this function right here is x squared plus 1. And I want to think ahead about what the derivative of that would be. The derivative of this would be 2x. And conveniently, we have a 2x right here. So that means for my u, I want to choose x squared plus 1. And then what I do next is I take the derivative of u with respect to x, and that equals 2x. Then, essentially what I'm going to do here is multiply by dx on both sides. So this is what I will use to substitute. So in this function, we have actually, how about I rewrite this so that I'm going to box off. So this integral turns into, I'm going to rewrite this to make it a little clearer. So we have x squared plus 1 to the 4th. I'm going to move the 2x over here, 2x dx. So this is the substitution we're going to do. So this is u, x squared plus 1, so that's u. Then, let's choose that. Then du is equal to 2x dx, and we've got a 2x dx. So when we do our substitution, this orange one right here turns into u to the 4th. And then this purple piece right here is just du. So now this is our new integral, and this is much easier to work with. So let's integrate that. So u to the 4th is just, that'll turn into u to the 5th divided by 5 plus c. And then last step is to just, we don't want to keep it in terms of u because our original function was in terms of x. So we just want to substitute u back in. So 1/5, and then u was x squared plus 1 to the 5th plus c. And that is our integral. And if you think about this for a second, just thinking about what the derivative of this would be, we would have to do the chain rule. So the 5 would come down in front and it would cancel with this 1/5. And then we would have x squared plus 1 to the 4th power, which is what we have up here. And then chain rule multiplied by the inside of this. So multiplied by 2x, and that's exactly what we have right here. So that's what I mean when I say this is the opposite of the chain rule. So let's take a look at number 2 now. So this is really similar. So again, well, actually the first thing I'm going to do here is rewrite this so that my radical is no longer a radical. I want an exponent, so that's what we've got. I'm going to let u be the inside of this composite function, x cubed plus 1, because I know when I'll take the derivative of that, it'll be 3x squared dx, and that's exactly what I want. So let u equal x cubed plus 1. And this secondary step right here, I tend to skip this just to save myself some writing. You just have to remember, so it's du equals 3x squared dx. So taking the derivative of both sides of this function. And now I'm actually all set to do my substitution. So just to make things clear again, we've got this piece right here is u. And this piece, 3x squared dx, is du. So when we rewrite our integral, I will have u to the 1/2 power, and then the 3x squared and the dx, that is all du. So we're just left with u to the 1/2 du. And again, that's much easier to work with than our original function there. So to integrate this, we add 1 to the exponent and then divide by that new exponent. It's a fraction, so I'll just multiply by the reciprocal plus c. And then finally substitute u back in. So 2/3 x cubed plus 1 to the 3/2 plus c. All right, so those were two sort of basic examples. So we'll just have two more just to really make sure we get what's going on here. Some things are going to be a little different about 3 and 4. You will see exactly what I mean. So just like last time, I'm going to let the inside of that function, that composite function, be u. And just thinking ahead, so the derivative of this is 2x. Now, we have an x here, but we don't have a 2. So let's see if we can figure out a way to get around that. So du equals 2x plus, oh, nope, not plus 1. 2x dx. So this is our derivative here. Now, if I divided by 2 on both sides of this equation, let's see what happens. So I would have 1/2 du equals x dx. Now, this is exactly what I wanted right here, x dx, because we've got an x dx up here. So that's actually perfectly fine. So let's see what happens when we do this substitution. So we'll have the integral of u squared, and then the x dx is equal to 1/2 du. So I substituted using everything we figured out over here. So again, that's u, that's u. So we have u to the second power, and then times 1/2 du is equal to x dx. And I'm looking at this, and it actually doesn't really cause much of a problem at all, because that 1/2, we can actually just pull that outside because it's a scalar multiple. So we have 1/2 times the integral of u squared du. And it doesn't cause much of a problem at all. So then we add 1 to the exponent. 1/2 is still hanging out in front. We're going to divide by 3 plus c. And that is equal to 1/6. I'll substitute the u back in now. X squared plus 1 to the third power plus c. So that is that one. And we have one more with a similar issue as that. So again, I'm going to rewrite this so that I don't have a radical. So 2x squared times x cubed plus 2 to the 1/2 dx. I'm going to let u be x cubed plus 2 du is 3x squared dx. All right, so we have a different issue this time. In our original function, we have a 2x squared, and down here we have 3x squared. So it's a different but kind of similar issue. We don't really need to worry about it too much because we know that we can divide by 3 on both sides, and that's fine, like we did in the last problem. And then similarly, if we want a 2, we could just, there's a couple things we can do, but what I'll do right now is multiply both sides by 2. So now I have exactly what I want. So I have 2x squared dx, and up here I've got 2x squared dx, and then I've got u to the 1/2 power. So that all works out really nicely. If you're wondering what the other thing you could have done was, you could have actually taken the 2 out right away, and that wouldn't change too much. You would still have to divide by 3 over here, but I don't think either way is easier than the other. So whichever makes more sense to you. So now it's time for us to do our substitution. So I'm going to do this without the colors this time. So this integral is equal to 2/3. I'm going to pull that out right away because we can. We know we're going to eventually, just like we did over here. So I'm going to pull it out at the beginning just to save myself some writing. So we have 2/3 u to the 1/2 du. And then I'm ready to integrate. So 2/3 u to the 3/2. And I'm going to divide by 3/2, which is the same thing as multiplying by 2/3 plus c. And then that is equal to 4/9. And then u was x cubed plus 2 to the 3/2 power plus c. And that is basic u substitution for taking the antiderivative of composite functions.